Welcome to another KStars focus tutorial. This one is going to concentrate on how you can analyze your autofocus runs to improve, hopefully, the parameter settings to give you better results. So I'm going to start off by showing you how to use the simulators, because there'll be a key part of the analysis that we'll need to perform in order to see how our autofocus runs are performing, and then potentially to try and improve them. So in order to set up the simulators, I'm going to create myself a new profile. So I shall call it demo. All you need to do for each of the devices that you're interested in is to go down to simulator and select the simulator. I suppose technically I don't need to set all these up for this demo, but it won't take long, so I'll just do this. So we've got a telescope or mount simulator, we've got a couple of CCD and guide simulators, we've got a focuser simulator and a filter. That should be good enough, so I'll create that profile. And then I'll connect to it. Okay, so it's asking me just to connect for the first time, so I'll do that. And it's going to give me the optical train pop up because this is the first time this profile's been used. So I'll just quickly configure this how I want it. So I've got on the primary optical train, I've got the focus, the telescope simulator, the CCD. There's no guiding of primary. This is my equipment, so I'll use that. I've got a filter wheel and a focuser. On the secondary, that's correct. I don't have a focuser or a filter on the secondary, so that's pretty much how I want it. Okay, so everything's set up in terms of the simulators. Now, one other piece of information that is quite useful is if you set a couple of parameters on, Ekos will log your focus frames for you, which you can then use for analysis. So under developer, the save focus images box, you need to tick that, and you need also to have the focus box here ticked in logging. And if you do that, then when you run autofocus, so I'm not going to do it now, but if you press that, what will happen is each of the images that that focus will take will be logged for you, and that's quite useful. So they get logged in a directory called Autofocus, which is at the same level as the logs directory. So, if you go to your logs directory, go up to its parent, which is KStars, then you'll find this Autofocus directory. So basically, each day has its own folder, and then all of the autofocus frames taken within that day are logged into this directory. So if you are going to turn logging or the focus frame logging on, just be aware that it will eat up a lot of your disk space if you don't take care of archiving the information periodically. So we've got a bunch of frames. What you'll need to do is identify a number of frames that are associated with an autofocus run. So I've highlighted a group here, so I can see the timestamps 0803, and we have 3, 4, 5, 6, 7, 8, 9, 10 frames. So each of those frames represents a data point. The way linear one pass works is, in this case, it will do a sweep of 9 frames, calculate the best focus position from those 9 frames and move to it, and then take a 10th frame at that optimum focus point. So I know from just looking at this that the way I have focus configured would be to take 9 frames, and they would be persisted along with the final frame, which is at the best focus position. So what I do then is I copy these frames, these 10 frames off to just a working directory somewhere, doesn't matter where. In this case, I've created a directory called demos, and imaginatively I've got demo 1, demo 2 and demo 3 directories that just contain one autofocus run. So the reason I've done that is that we can then go back to the simulators, and we can have a look at the CCD simulator, and under the simulator config tab at the bottom are a couple of fields that are going to be quite useful. So this directory field here allows me to just type in a directory. So if I put demos, demo 1, set that, you can see it's been set there, and then enable the directory, it gives me this message saying that subsequent exposures will be loaded from this directory, the demo 1 directory. So that's quite powerful now, because I can run the simulator, and what it will do is it'll pick up in turn each of the autofocus frames in the demo 1 directory and play those into the autofocus routine. So that will enable me to rerun autofocus as it would have been when I collected the data, so maybe 2 a.m. in the middle of the night when I was imaging a couple of weeks ago. So we'll just go back to focus now. There's a couple of other things you'll just need to set up before we can run it, but these parameters here look okay. I'm going to use linear one pass. I'm going to use SEP because I'm going to be talking about that a bit more. I have created myself a profile. Now, what I've done with this profile is, if we compare it back to the focus default, there's a lot of things that are filtering stars out in the default profile. So I guess if I just adjust those so that they're roughly the same. I think that's roughly correct. Okay. So we're going to be using pretty much the standard profile. I've just created the same parameter set in my play profile. Going back to the mechanics now, I happen to know that when I did that focus run a couple of weeks ago at night, I had the walk set to CFZ's shuffle. I need to put 9 steps in here. I have 10 focus frames, which means there's an inner sweep of 9, so I need to make sure that's set to 9. If you don't match this number up with the number of frames in the directory, then you're going to get a mess with autofocus. So it's very important that you match this number to what's in the directory that the simulator is going to be reading the data from. And that's about it, I think. So I'm going to hit auto. I'm just going to start this off at around 18,000. So my real rig solves at around 18,000. So I'm just going to start it at around 18,000. So I'll hit autofocus and we'll watch it. So what this is doing is it's picking out my real world data and it's playing it back in simulation mode in the Focus module. So this is quite powerful because you can do this yourselves with your data. So you can, you can take some of your real focus frames. You can set up the simulator as I've just done, and you can then do what I'm doing, which is to replay that data, through the simulator in order to give you some good results, and then hopefully adjust some of these parameters and get even better results. So this is what it's done. I think the first thing I would do is I would have a look at what is actually being solved. So you can zoom in and you can kind of see what it's picking up. So we can see it's sort of picking up a star here, but it's not picked this one up, it's not picked that one up, it's not picked that one up. So it's missing a load of stars. Okay, that's the first sort of obvious thing. The stars it's picking are kind of the brighter ones, as you'd expect. Now, this is quite interesting. So this is a saturated star. It's obviously massive. Including it in the HFR calculations would not be a particularly sensible thing. And this is where this saturation parameter of 90, I've got it set to 90, you could probably up it to 95 or something, but I'm basically excluding that because it is saturated, which is what you'd want to do from a focus perspective. If I go all the way down into the corner, I mean, I'm getting round stars in the corner, so that's good. It does mean my field flattener is doing its job. It's flattening the curve all the way out to the edges of my sensor. If that were not to be the case, what I would do is I would put a ring mask on. So, for example, if I set this to 80%, what'll happen is that Focus will only look at stars that sort of within the 80%. It won't look into the corners. So if you do suffer from elliptical stars out in the edges of your frame, then you can easily deal with them by putting this ring mask on and making sure that the stars you have inside the ring mask are good stars. Now I don't have that problem, so I don't need to do that. So the most obvious thing is there's a lot of stars being missed out. So the reason there's a lot of stars being missed out is that I'm filtering down to a relatively small number of stars. So I'm initially only taking 250, running a load of processes, and then taking the brightest 100. So I can easily sort of stop that. I can put this up to a big number, make that 10,000. I'm also filtering out sort of brightest and dimmest stars. I don't think there's any great benefit in doing that. Max size, I've got a max size of 10, which would deal with big stars, but I don't think that I'm going to see much benefit of doing that, so I'm taking that off. Going back up to some of the SEP parameters, I think it's worthwhile just taking a minute to describe very basically what SEP does. So what SEP does is to divide each pixel into either a background pixel or what it calls a source. A source would normally be a star, but it's anything that's not background, so it could be a galaxy or a piece of bright nebula. And then what SEP will do with the background is it'll calculate an average background intensity and a standard deviation. So, it might be, 8 an intensity of 8 plus or plus a standard deviation of 1.5 or something like that. So if you look at, if you zoom in on the background, you can see, I can do it here with the, you can see as we get further and further in that each of the pixels, does have a different value. Some are obviously brighter than others, and the way SEP looks at background is to work out the average, work out the standard deviation, and then to use this number here, in this case 2. So it'll take the average value of the background, add 2 standard deviations to it, and then any pixel that is above that value would be a candidate for being a source. Anything below that is kind of ignored from a source extraction perspective. So the higher we set this number, the less noise we'll get, which is a good thing, but the less sort of dim stars we'll get as well. So if you have a lot of stars, you can probably get higher quality stars by setting this number a bit higher. If you're very low on stars, you could play with reducing this number a bit to get you more stars, but the risk you'll have is that you'll be detecting noise as stars rather than real stars, which obviously you don't want to do. So 2 is a good number to start with. I would say, given I've got a lot of stars, that I'm going to put that a bit higher. The next one to kind of look at is this min area. So this is the number of contiguous pixels that SEP requires to be above the background threshold in order for the source to be deemed, a candidate source. So think of it like this: 20 pixels is really just a block of 4 by 5 pixels. So if 4 by 5 pixels are all above whatever the background threshold is that you've set, then that would be considered a source. If you've only got 19 pixels, contiguous pixels above that, then even though it may be a star, that would be rejected as a source. So again, if you up this parameter here, you will get rid of smaller stars and will only be looking at at larger stars. So 20 is a reasonable number. Could go a bit higher. I'll try just a little bit higher. We'll come back to the convolution filter because this is quite powerful, but it's a little tricky to set. The rest of the parameters, in my experience, don't make a lot of difference to focus. The deblending is all about, if you have 2 stars very close together, SEP will attempt to apportion some of the pixels, so a pixel into star 1 and star 2. So the space between the 2 stars is obviously the sum of the intensity from both stars, and the way you set some of the deblending parameters will help SEP to do that deblending of multiple stars. I think from a focusing perspective, I don't personally think this makes a big difference. Photometry, I would leave these alone. This is most of the stuff here has very little bearing on focus, so I don't think it's worth playing around with them too much. But obviously, you can, with this approach, you can fiddle with them if that's what you want to do. So I've made a couple of adjustments, so we'll just apply those. Now the beauty of this is I can just rerun this. So I've made a couple of parameter adjustments and I'm now going to rerun focus, and once again it's going to use exactly the same set of data. Now the beauty of this is I can sit here for as long as I want, just playing with these parameters to get to a set of parameters that give me the the best possible focus curve. And what it does mean is that you don't have to waste imaging time doing it. You can collect the data to do the analysis in parallel with imaging without interrupting your imaging at all, and then you can do this without having to have your rig connected at all. I'm just doing this on a standalone laptop, so it's quite a nice tool. So that's probably maybe minimally different. It's not made a huge difference. One thing it has done is it's used a much larger number of stars, which is fine. If you're on a computer which is a bit limited in terms of processing capability, you can use these. You can put these numbers down to smaller values to process less stars, which will be less compute intensive. But other than that, generally you're going to get a better result with more stars rather than fewer. I'm just going to mention the convolution filter now. So the default filter, so convolution, this convolution filter is very much like applying some sort of convolution in other post-processing astronomical software. It will basically take whichever filter you've set and it will convolve it with the image with a view to trying to pick out things that match the filter. So the default filter is really just a sort of a plus sign or a cross. It's a very basic filter. And it will scan across the image and it will look for things. It'll enhance things that look like a cross, and that will help the star detection system pick out stars as opposed to things that don't look like the cross. The other filters that are available are Gaussian. These two sort of hat filters. I'm just going to talk about the Gaussian filter. So what this is going to do is it's going to create a filter that is of a Gaussian shape, and you need to give it some sort of full width half max value. Now in the manual it says, or it recommends, starting with something that represents the seeing in pixels. I haven't really found that to be great, but it's a place to start. What I happen to know is that I get reasonable results if I set this to around about 3 or 4 on my equipment. But again, we can, on your equipment, you can set this to 3, run it, 4, run it, 5, run it, 6, run it. Only takes a short amount of time to run each time, and you can see what effects you get. So we'll just apply that and rerun. I think so. The idea behind selecting a Gaussian is that for a focus frame that will be a couple of seconds, stars should be somewhat Gaussian in shape, and therefore using a Gaussian filter ought to be better than using the default filter. Now I found on my equipment that is actually the case. I've tried with other folks to do to suggest they use Gaussian, and some people have seen benefits and some haven't. So it's a little unclear to me as exactly why it doesn't work for everyone, because I think theoretically a Gaussian shaped filter should be more effective than a simple sort of cross shaped filter, but as I say, it doesn't seem to be the case. So this is a good curve again. Because we've put a Gaussian on here, we're getting slightly fewer stars than when we had the default filter, but because there's so many available on my rig, then that's not really a problem. if you do increase this, you will see the number of stars, this full width half maximum parameter. You will see the number of detected stars starting to fall off, because obviously what you're doing is you're trying to convolve the image with a bigger and bigger Gaussian. So it's it's going to be pulling out the bigger stars and doing not reinforcing the smaller ones. So this is another way of sort of biasing the filtering to larger stars by upping the full width half max parameter. So as I say, you can play around with this as much as you want and adjust these parameters as much as you want in order to try and get a better solve. My data works pretty well on my rig anyway, so the benefits of doing this aren't particularly obvious here. What I would just mention is I put the use weights and the refine curve fit off for the purposes of this. These will help your real world solving, so I would always have them on when you're imaging. The reason I've taken them off is because they're performing some statistical work on the data. They will compensate to some degree for less good data. So I wanted to sort of run the various runs with the different set parameters without the benefits of the sort of the compensatory statistical work that these two options provide. But from an imaging perspective, I would always have them on because they will help you get a better curve fit. What I'll do now is I'm going to go and look at some other data that is not my rig, but it is real world data, and it might be relevant to obviously other folks. So what I'll do, I'll go back to the Indy pop-up and I'll have a look at demo 2. So just put demo 2 in here, set that, we enable it, and it says we're going to be using demo 2's data. So just have a look at demo 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 frames. So we'll go back to focus, go into the mechanics. So there's 13 frames and one for the final positioning frame at the optimum focus position. Now I happen to know that this set of data was taken with the classic walk. Now from an analysis perspective, using the simulators, I would not recommend you use that. I would use the fixed steps, because the classic walk has some heuristics in there to tell it when to stop, which are quite sensitive to how the star detection etc. is going. So as you play with the data, you will get a different number of steps, only by one, but the problem with that is that you need to match the number of steps to the number of focus frames you actually have. So I would, if you took your data with the classic walk, I would always use fixed steps, because that will guarantee that you will always get 13 steps. So we'll just set some of these parameters back just to, okay, so I think I've set these parameters up how I want them to, so we'll just run this now. So this is the second demo 2, the second set of data. So this is a long focal length RC, so as I mentioned, with a central obstruction. So obviously the concern with the central obstruction is donuts, a long way out of focus, so we'll see how we go with that. So it's an okay V-curve. It's not great. What I normally look for is, so the R squared's 0.90, which is, it's okay, but it's not great. It's not too bad on the way in. This isn't great around the minimum, and then obviously points 12 and 13 are a bit odd, in that, as opposed to sort of being up here, they've sort of moved down a bit. So that's all worth having a look at. So again, what I would do is I'd sort of zoom in a bit and just kind of see what's happening. So I mean, there's quite a bright star, probably saturated. Our 90% saturation limit is preventing us from picking that out. This is quite interesting. So this is obviously some sort of galaxy, and so star detection has found, I can't really read it, but it looks like there's 2 or 3 things it's identifying as a star in there. The way to probably deal with that is to put this back to something that would take anything that's very elliptical out. What else can we see? Yeah, I mean, the rest of it doesn't look too bad. One thing you can do is you can just take a frame, and what it'll do is it'll just advance through, if I keep clicking this, it'll advance through the sequence of focus frames in the demo2 directory, and it'll show you the results, which can be quite useful. What I'm going to do is I'm going to go over to points 12 and 13. So this is more like the stuff at the minimum. If I zoom out, that might be more useful. So we're through the minimum, and we're starting to okay, I think that's probably about 0.11. I think that's frame 13. So these 2 points are obviously dipped off, so it'd be interesting to kind of see if we can figure out why. Now, as you can see here, there's a couple. This is, I think, probably 1 star, and if I zoom in a bit more, it might be clearer. You can see it's printing several numbers, which indicates it thinks there's several stars there. And that kind of shows it up reasonably well. So what's actually happened here is you've got the donut that you normally get with a scope with a central obstruction, but it's the donut itself is starting to break apart. So it looks like there's almost 4 individual quadrants of the donut, and I suspect what's happening is star detection is detecting each of those quadrants, or maybe not all of them, but certainly some of those quadrants as an individual star. So what you'd end up with maybe at points 10 and 11 is that donut is hanging together and it's being detected as a single star with an ever increasing HFR. And then points 12 and 13, what's happening is the donut is starting to break apart, and the star detection is detecting fragments of the donut, and those fragments are starting to become smaller than the original whole donut in data points 10 and 11. So that's why we're starting to see this strange behaviour over at points 12 and 13. Now, there's a couple of ways to deal with it. One is not to go that far out of focus, that you start to get this problem, and that's probably the best way to deal with it. But you can actually deal with that a little bit with the parameters. I wouldn't want you to think that you can deal with donuts per se by adjusting these parameters, but certainly if you're on the boundary of having problems like this particular run is, I think by adjusting the parameters a bit you will get a better result. So we'll see if we can do that. So the first thing to say, I think, I would probably just up this again. I'm not sure this is strictly necessary, but we don't want to be fishing around in the in the background too much. But I think the thing that will make a bit of a difference here is going to be trying a different filter. We'll set the full width half max up to say 5, and we'll see if by doing this we can force the star detection to not see this fragmented donut as multiple stars, but as an ever increasing bigger single star. So we'll just apply that and run again and see how that goes. So we're on this star, and you can see, as the okay, so a couple of things. So the fragmentation here is being dealt with better by the Gaussian filter than it is by the default filter. So these final points are not sort of dipping off as they were. If you're wondering why is 0.1 all the way down here, this point it's kind of my fault. What I didn't do was set the Indie library counter back to the beginning after having played around with the frames. So what's actually happened is it started one frame off where it should have done. So what I'll do is I'll just set this again, and hopefully we won't see this problem on the next run. So I'll let that run, but I think whilst that is running, we do see that the Gaussian filter looks to be doing slightly better on this. I think again, depending on how some of these outer points go, we may need to tweak the threshold, and the min area would be the other thing I would look at. So that's better. So it's tracking. 0.7 looks slightly off, but that's just how it is. These other points are tracking quite well. Points 12 and 13 now don't curve off the line as they did on the original. They're tracking that line a lot better. If we kind of zoom out and then zoom back, the other thing I think I've fixed is we're no longer detecting anything in this galaxy by setting the max ellipse here to some reasonable value. So that's sort of not getting polluting the results now. So I mean, that certainly improved that run. I think one other thing's probably worth just showing. I'll run it again just with these two things on. Let me just reset this again. It can be a bit temperamental, so it's always worth just resetting it and then rerunning. And hopefully what this will show is that we can maybe get that R squared up to 0.99. I suppose the other thing to say is, you know, I'm only looking at one set of data, and what may work great for one set of data, you know, may not work on your next focus run. So, you know, when you're doing this yourself, don't try and squeeze that last fraction of a percent of benefit out of, you know, the data from one run. I'd run it across, you know, several runs and see where you get to. So I think by putting the use weights and the refined curve fit on, what we've done is we've got a better fit of 0.99. So it's taken out that point and that point, which are kind of off the line slightly. You can see that, and it's got you quite a good curve fit there. So that's sort of the second set of data. So what I'll do now is I'll move on to the third set. So we want demo 3 now. So set demo 3, enable it, and subsequent exposures will be loaded from demo 3, which is what we want. So back over to the focus simulator. Now I'm going to reset the parameters again to what they would be if you're using the sort of focus profile. Put this back. Okay, so as you can see, the solution here is not great. Points are quite a way away from the curve. It's not the best curve it's tried to fit either. The R squared is quite low, 0.66. So what I would start off by doing is just having a look again at some of the points. So here we are in the top corner, and these stars don't look too bad, so I don't think we've got a flat field problem particularly, so I wouldn't mess with that at all. If I just advance this a frame, this will take us to frame 1, which is the most out of focus. So here we can see some donuts. So you can see this this piece of the curve is very flat, and we are seeing the same problem we saw previously, which is that whilst that donut has been detected at, you know, 7.5 pixels, this one is being detected as at least 2 parts of the donut with much smaller 2 point something HFR. So that the effect of this is dragging these 2 points down, and so as opposed to them being much higher up, you know, they're much flatter. So that's the standard donut problem we saw before. So what I would do there is I'd put try the Gaussian filter, and what I tend to do is I look at where it kind of should be on the sort of, you don't want to go too far out, but you know, if we look at say 0.9, you know, that's around 5 HFR, so double that for the full width half max. Let's try 10. I think, yeah, it's detecting some reasonably faint. I'll go through a bit more, bring it back into focus and see how the star detection's looking when we're a bit nearer focus. Okay, I mean that's okay, I think. I mean, these are quite faint stars, so maybe you know, let's just up that a bit more, so we're maybe not so worried about these smaller stars. Okay, apply that, just go and reset. Run it again, see what we get. Well, that's a bit better on the donuts. You can see the donuts are getting detected as single stars, which is obviously what you would ideally want. I mean, again, ideally, probably with this, I would suggest not taking the focuser so far out of focus that those donuts are quite so pronounced. But again, you know, you can see that to some level we can compensate a little bit for donuts by adjusting the parameters. Well, that's better. I mean, you can see there's a massive difference now in these first points. I mean, maybe I've overdone it slightly, but anyway, there is a massive difference here. We've still got a reasonable number of stars down around the point of focus, so that's good. And we're up to 0.97 on the R squared, so I would say that's pretty good. I mean, you could tweak these numbers around and play around, you know, as much as you want to get the result as good as you can get. You know, again, I'll just run this one more time with the use weights and refine curve fit on. I suppose one thing to say, the Gaussian filter is slower. It's doing more work than the default one, so if you do want to try using it, you know, you will need a bit more compute power to not have to wait a long time for it to complete. Okay, well, it's knocked that last point off, which is interesting. And it's got a curve fit, a much better curve fit. So, you know, I think that's probably an improvement. So that's kind of it, I think. I wouldn't necessarily use any of the numbers that I've put in here as absolute numbers. What I have found from looking at a number of people's focus frames over, you know, a few months is that it's very difficult to be prescriptive as to what to set a particular parameter to. Different setups seem to work quite well with certain values and don't work very well with other values. So I think really what you need to do is a bit of experimentation. But the whole purpose of this, I think, just to reiterate, is that you know, using the simulators with your own focus frames will enable you to tweak your own setup. And the advantage or the beauty of it is that you can do this, you know, in your own sort of downtime. You don't need to disrupt any imaging time to try and improve this. And of course, if you play around and find that, you know, your parameter setup actually is as good as it's going to get, then that's fine. You know, you can continue to use the focus default profile and just ditch your play profile if that works great for you. The other thing I would suggest is, if you are going to play with the parameters, one of the things I have seen is that you know, you can tweak the parameters to get a really good result on one run, and you know, when the conditions are a bit different, the new set of parameters may not perform as well as you would want. So if you are going to play around with it, I would try and advise you to take a few sets of data and make sure that the settings that you use work on, you know, a range of different sets of data, you know, before you you know, start implementing it into an imaging session. But hopefully this will give you an idea of the sorts of parameters you can look at, and hopefully you can improve your focus setup. Thanks, and see you next time.